So before we move on, let me just tell you, I'm not going to do this explicitly because I might include this in an assignment. But so I'm just going to tell you about a variational principle. Okay. So how many of you have done classical mechanics, like not like in terms of Lagrangians and Hamiltonians and things like that? Some of you haven't, I know. So, okay. So the idea is that sometimes in physics, it's good to have a different point of view about the same thing. So for example, in the fundamental equation of classical physics, classical mechanics is Newton's law, right? Which is famously known as F is equals to ma. M dot x double dot, right? This is, so let me just, this is Newton's law. And this is a second order differential equation. But there's another way of formulating classical mechanics known as the Lagrangian, the principle of least action. And you define some object called the action, so S here is not entropy, and it is given by the time integral of the kinetic energy, let's just call it Ke, minus the potential energy. So from some initial time to some final time. So the idea is that you have some initial time, an object at some spaced point x0, and at final time, the object ends up in some space point x final. Now, depending on the potential, depending on the forces that are acting on the object, this guy can take some path. We don't know what the path is, right? So what the principle of least action tells us is that it asks the question, what is the physical path that the particle will take? And the principle of least action tells us that the path that the physical particle will take is the path which extremizes the action. That is, if this is the physical path, and you do a small variation of this path, then of course, what it'll happen is that the value of this integral will change because this integral depends on which path you're taking. So that means this S will change. And the principle of least action, says that the physical path is the one around which a small variation of the path leads to a maxima of the action. And you can show that this equation is equivalent to Newton's law. But whereas Newton's law is a differential equation, this is an integral equation. This is an integral principle. So this is just an example of a variational principle way of reformulating mechanics. So in thermodynamics, you can also do similar things. And that's why, so, I say all of this to kind of motivate what's coming after. So you don't have to know all of this. At some point, you will take a classical mechanics course and you will learn how this is done in full glory. And if you stay in physics and you do graduate studies and learn about quantum field theory, you will also see how this beautiful picture is generalized in quantum mechanics. And it was generalized by Dirac and Feynman. But here, I just want to tell you about the variational principle in thermodynamics, or in statistical mechanics, to be more precise. And we saw that in the case of the microcanonical ensemble, the way in case of the microcanonical ensemble, the principle, the fundamental principle led naturally to maximizing the entropy, right? Because the physically realized system was the one that in which maximized the entropy. So it turns out that you can also formulate the canonical ensemble by a similar entropy maximization condition. So it's just that the difference between the entropy maximization for the microcanonical ensemble and the canonical ensemble is that you maximize the entropy, but subject to different constraints. Okay, so you basically have some kind of a function which is the entropy. So this is the Gibbs expression of entropy. And then you have some Lagrange multiplier that you add to it. Okay, and then you maximize with respect to the probability for this entropy, and then you maximize the Lagrange multiplier with respect to its variable, and that gives you the depending on the constraint, it gives you either the microcanonical ensemble and the canonical ensemble. So what are the constraints? The constraints turn out to be, so for so alpha is some constant. It's the auxiliary variable in your Lagrange multiplier. By the way, do you guys know what Lagrange multipliers are?
No, sir.
Okay, so let me just tell you what it is. So for the microcanonical ensemble, this term L is alpha times sum over n Pn minus 1. So this is the constraint. The constraint is saying that the sum over P has to sum up to 1. The probability has to be 1. So this gives you the microcanonical ensemble. But for the canonical ensemble, the constraint is different. And the constraint is that the average energy, which is EnPn, has to be equal to some constant, and that constant is, we call it E. Okay, and that gives you the canonical. So this is some constant. I'm just calling it. So of course, we are not assuming that this is equal to this. We are not assuming that the sum of the Pn is equal to this. That's what this constraint does. So now if I take W and I write the equation, if I solve this equation, this is so let me use n here instead of a. So this is one equation. The other equation is that, so this is the equation which is kind of maximizing the entropy, but simultaneously we also have to impose this equation. And what is this equation? This equation is telling me that is it exactly that if in the first case, it's telling me the sum over the probabilities is 1. If it's in the second case, it's telling me that the average of the energy is equal to some constant, which we are calling E, the average E, right? So this is a variational principle for deriving both the canonical and the microcanonical ensemble. So in case you haven't seen, Lagrange multipliers and things like that, don't worry about it. What I'll do is that I'll just write out a long kind of, assignment so that you can explore these things, okay? So this is a little bit of a tangent. But, I can answer questions, so it's not like, I don't want to stop you from asking questions about it. So here, you have a better view of the whole thing.
So what's the W in the equation? W is equal to S plus L.
Right, W is defined that way. S is the Gibbs entropy. So S is the expression for the Gibbs entropy that we saw, the original expression in terms of probability. So the idea is that, you want to derive that the probability of the microcanonical ensemble is that it is 1 divided by some constant, right? That is basically what you're, and for the macrocanonical, so not the macro, sorry, for the canonical, you want to derive that P alpha is given by some Boltzmann distribution, right? This is what we want to derive, okay? And what I'm saying is that if I take this W and and maximize and solve these two equations, the first equation is that maximizing the quote-unquote entropy with this term, and the second one is imposing this constraint, which is what the second equation does. Then these two equations, if I solve them, should give me, depending on which constraint I take, either this or that, okay? So that's the idea. Okay, so this will be an exercise in their next assignment.